Good afternoon, everyone. So in the last class, we were talking about the hydration kinetics of how the different phases of cement compounds actually start reacting and what factors actually affects the rate at which the reaction happens. Okay. We also saw that the reaction of the cement is not happening in water, but it happens in a pore solution. And the pore solution is composed of the ionic species that you get when the cementitious compounds start dissolving into the water. The only ions that remains in the long term in an appreciable concentration are sodium, potassium and hydroxyl ions. So ultimately there is a charge balance that gets maintained. Okay. We also briefly discussed how the pore solution can be obtained. You need to do a proper compression of your concrete, hardened concrete, and extract the pore solution. Of course, to do the chemical analysis, you will have to dilute it many number of times to obtain sufficient sample to do a proper chemical analysis. Just for the record, generally what is done for ionic determination is absorption spectroscopy, and that's how you'll actually get the numbers for the amount of sodium and potassium and so on. For the anions like hydroxyl ions and sulfate ions, you'll have to do ion chromatography or other methods which can help you determine the correct extent of the ionic species that are present. So it's a little bit an involved procedure. However, there are also guidelines to look at what can be an approximate pore solution composition based on the initial cement composition. That means the initial oxide composition of the cement can be used, and you can actually do a simulation to determine the approximate pore solution composition. And this is again made possible by some work that is done by NIST, N-I-S-T. Remember I talked about them earlier. That's the National Institute of Standards and Technology based in the US. And they've done some work where they've actually done simulation based on the original cement composition, generating the actual pore solution composition. So, I mean, most of the people around the world don't use pore solution extraction as part of their research activities. They have to actually fall back on something which is available that can approximate that aspect. That means how to obtain the pore solution without really doing this extraction, which is a very cumbersome process. Okay. So anyway, we looked at this, and there's also a lot of research which looks at how the pore solution varies when you substitute cement with other sorts of systems. For example, here there's a lot of different concretes which have been tested for their pore solution based on these concretes are entirely made with CEM1 or Portland cement. This is actually from a research paper by Rosen et al. So again, these numbers are fairly well corresponding with what I presented to you earlier in the previous slide. So it shows you basically with the passage of time. So on the x-axis there's time, on the y-axis there's concentration. So with the passage of time, how much are these ionic species actually changing? Okay, and you can clearly see that if you look at sodium, hydroxyl and potassium, there's a constant increase in the ionic concentration in the pore solution, whereas for sulfate there's a decrease, and silicon is more or less constant, but if you look at the numbers, the silicon concentration is very low. All the others we are talking about hundreds of millimoles per liter, okay, but silicon is of the order of 0.1 to 1 millimole per liter, because silica is not essentially soluble. Okay, it's not easily soluble. Because of that, it does not come into the solution, but you can have some limited solubility available from the silica also. Now what happens when you have blended cements like fly ash cements or slag cements? What is presented here is a silica concentration. Now we expect that because fly ash and slag have amorphous silica, there may be a little bit higher silica content in the pore solution. So that's what is being shown here in terms of the silica concentration with respect to the pore solution. So you do see that there is a minor increase in the extent of silicon concentration which is available in the systems as compared to what you have in the cement system. Okay, but nevertheless, there's not so much silica available because it's not in the soluble form. There's definitely more silica concentration in slag systems than fly ash systems, and that seems to indicate the better reactivity of the slag systems also. We know that slags are much faster reactive as opposed to fly ash. Of course, what is not shown here is how the ionic concentrations, that is sodium, potassium and hydroxyl ion concentrations, change when you have blended cements. What do you expect will happen in the case of the ionic concentration?
Decrease.
It will decrease or increase. Generally, the alkali concentration that is contributed by cement is far greater than what is contributed by fly ash or slag. So when you replace part of cement by fly ash or slag, you're going to be reducing the alkali concentrations. So that is actually a very positive aspect in one way, because having a lower ionic concentration also means that your system is less conductive. And why is conductivity important? Because when you have some phenomena like corrosion, for propagation of corrosion, the medium surrounding the steel, if it is more conductive, then the rate of corrosion can be much higher. So with blended cements, one of the primary reasons why we see a reduction in the rate of corrosion is because our system is more resistive or less conductive as compared to ordinary Portland cement. Okay, so having looked at pore solution, now let us look at how these products are actually formed. What sort of structure is there for the CSH, calcium hydroxide, ettringite, monosulphate, etc. And how do we look at the porosity in the system? In what ways can water be held within the cement paste? So hydrated cement paste is simply composed of the capillary pores and the hydration product. So part of it is solid, part of it is porous. Okay, so porosity contributes a part of your hydrated cement paste. Of course, if the pores are small enough that they are within the structure of the CSH, then they are called gel pores. If the pores are exterior to the structure of the CSH, they are called capillary pores. Larger pores are called capillary pores and smaller ones are called gel pores. The general distinction is that capillary pores are typically greater than 10 nanometer in size, okay, or always greater than 10 nanometer in size, whereas gel pores are less than 10 nanometers. So that is generally acceptable as a distinction between capillary porosity and gel porosity. Now of course, as the pore size becomes smaller and smaller, it will become all the more difficult for any liquid to propagate through these pores, right, because you know very well from your capillary rise equation that the capillary diameter is inversely proportional to the pressure. When you lower the diameter, the pressure increases, right. So you need greater amounts of energy to push in water through smaller porosity. So obviously that is why smaller pores or systems which have lesser porosity are more durable, because you can't allow water or other chemicals to pass through these compounds easily. So gel pores are generally present within the structure of your CSH, because only CSH is the semi-crystalline material. All the other compounds like calcium hydroxide, ettringite, monosulphate, they are well developed crystals. So generally gel pores are present within the structure of your CSH, whereas capillary pores are present outside the structure. According to Powers, once again, 1/3 of the pore space is composed of gel pores and the rest are capillary pores. So I have told you before, Powers was one of the premier scientists who worked in cement chemistry, and his work was primarily done at the Portland Cement Association in the US, and the kind of work that they produced actually still holds very good, because the kind of experimentation that was done in those days, top class, and because of that a lot of researchers still fall back on the that were proposed first by Powers. I think that was in 1940s and 50s, quite a long time ago. But despite the increase or advances in our scientific achievements, the extent of understanding we have seems to only keep confirming the kind of theories that Powers was able to propose 70, 80 years ago. Okay. So that shows you the extent of the class of his work. Anyway, so as per Powers, 1/3 of the pore space is comprised of gel pores and the remainder is the capillary pores. Now, which porosity do you think will play a large part in your mechanical properties and durability? The capillary porosity, because it is easily accessible. So if water has to get absorbed or water has to permeate through the concrete, it will go through the capillary porosity, not through the gel porosity. So some examples of cement paste microstructure are presented here through micrographs taken with scanning electron microscopes. Okay. On the left you actually have a micrograph which is actually showing you a fracture surface. So here a cement paste sample was taken and fractured. Okay. I think it is a cement mortar sample, not a paste sample. It was taken and fractured and directly put under the scanning electron microscope. So what you are able to observe with the help of fractured surfaces is the topology or the morphology of the hydration products that are actually forming. Okay. So here this is a low magnification image on the left and a high magnification image of this area that is marked on the left side image. Okay. So if you look at the high mag image, what we are zooming in on is a cluster of calcium silicate hydrate. The problem here is you can't simply distinguish one set from another. It is present like a fibrous mass. Okay. And how do we confirm this calcium silicate hydrate? This point analysis is confirming it's calcium silicate hydrate because it gives you peaks for calcium and silicon when you are evaluating the X-rays that are coming out from that point. Okay. So that's basically the spot analysis that is typically accompanying scanning electron microscopy. So we look at the X-rays that are coming out from the sample and look at the elements that are composed, that are present in that sample. On the right side is a slightly different image. That's actually a cement mortar which has been polished, and you're looking at a polished surface, not a fractured surface. So look how different it is. On the left side, you're actually able to see the hydration products in terms of their crystals or crystalline morphologies. On the right side, you only see a color difference between different phases. This is more or less similar to your optical microscopy, where I showed you previously that the phases that are brighter will reflect more light. So in scanning electron microscopy, the phases that are denser will simply reflect more electrons. There are more electrons coming off, so those phases appear brighter. I showed you previously also in the SEM picture of your inner CSH, right, inner outer CSH. So here you can clearly see these are aggregates here. The larger pieces are your fine aggregate or siliceous aggregates. You have the white unhydrated cement particles because those are the densest. Okay. You have the grey area around the unhydrated particles. In this case, you are not able to distinguish very clearly what is what. But if you look very closely around this spherical pore space, you will see that there are well defined deposits of calcium hydroxide which are lining the pore spaces. That is a very common finding in most cement based microstructure, is that you will start seeing calcium hydroxide in locations where there is free space available for its growth. So here it is growing in porosities. You will often find it growing in the interfacial transition zone between the paste and the aggregate, because we have discussed this earlier. Even in the ITZ, you have greater porosity around the aggregate. So wherever there is more porosity, you will tend to see more calcium hydroxide deposition. Okay, so here you are seeing calcium hydroxide. Again, how do we confirm it's calcium hydroxide? We are looking at the X-ray signal which is coming out of it, and it's showing a peak for calcium, okay, and of course oxygen. So that's how you can look at distribution of your hydration products. Okay, moving on, a little bit more descriptive here. On the left side, you actually have a C3S mortar. So instead of OPC mixed with water, you have C3S mixed with water to make this mortar. Water and sand, obviously, it's a mortar. So you can see the sand particles here, right? And the paste in between is only composed of hydration products of C3S, which is CSH and calcium hydroxide, right? C3S plus water gives you CSH and calcium hydroxide. So again, you can see the phases which are looking quite different. You see here the unhydrated cement grains. Some remnants of the unhydrated cement grains are there. Unhydrated C3S grains, only the remnants are there because part of the is hydrated. It is showing very clearly the inner CSH. Away from it, slightly darker, you see the darker grey phases. That is your outer CSH. And also there are brighter whiter phases here which are not as bright as the unhydrated phases. What is that? Not as bright as unhydrated phase, but brighter than the CSH. That is calcium hydroxide. Okay. So these brighter particles are calcium hydroxide. You can also see around the aggregate there seems to be a layer forming of calcium hydroxide, right? And there are several grains of C3S which are partially hydrated. Okay. So what I am trying to show here is a system where there is no aluminate present. So you will only get CSH and calcium hydroxide. Again, what sort of image is this? Is this a fractured image or a polished image? Why do you say it's a fractured image? You can't see any crystalline morphologies. Only what you're saying is a difference in the gray levels. So it's a polished surface image. Okay. When you see only a difference in the gray levels, it's a polished surface image. When you see, like in the previous slide, you actually see the morphology. Look at this left side image. You can actually see the gaps and crevices and the flaky and fibrous crystals. So that's actually a fractured image. You see that there is cracks here. Okay, that cracking may be shrinkage cracking, we don't know. The cracking also may be because of specimen preparation for the SEM. So while polishing, you have to really abrade it against very fine diamond paste, and before abrasion you also need to ensure that the specimen is properly dry. So when you dry it in a very high temperature, you are bound to also create cracking in your system. So very often when you use scanning electron microscopy to look at growth of cracks, you can get a lot of errors because much of this cracking could be attributed to the specimen preparation rather than any phenomena happening inside. Okay. So that's basically some example of C3S. On the right side, you actually see a microstructure of concrete. There are larger particles probably belonging to coarse aggregate, but may even be fine aggregate, because you see this much is 200 micron. So we are looking at probably about 600 micron on this side and maybe about 1.2 or 1.4 millimeter on the other side. It could be a particle from the fine aggregate also. Okay. These are definitely fine aggregate particles. Why do I say that? Because they are nicely rounded. Mostly river sand is used as fine aggregate, you can find highly rounded particles, and they have almost a constant phase. That's because most of them are quartz, silica. Okay. Silica will give you that darkish color under the polished section imaging. You can now see the paste inside. This is the paste in between the aggregates. How much do you think is there in this image? What area, what extent of area is being occupied by paste in that image? I would say close to about 30%. Yeah. So now what we've been talking about previously is that because of packing effects, you have a slightly different density of the paste close to the aggregate as opposed to away from the aggregate. Now looking at this microstructure, how do you define what is close, what is away? Can you see from this microstructure, for example, which is of course I don't have the magnification here, I only have the length bar or length indicator, but what do you think there is any interfacial transition zone present here? In this picture, can you see it?
It's there. The space between those four.
On this side, right? There is some space there. But do you see any difference in the gray levels of the paste close to the aggregate and away from the aggregate? You do. Maybe I didn't look at this picture well enough. So you can see the extent of paste that is between those four small aggregates is extremely less. And all of it seems to be more porous as compared to the zones here. Okay. My contention was, and so is the contention of several people who are against the concept of this ITZ, is that the spaces between the aggregates is in any case not large enough for us to distinguish different properties of paste near the aggregate and away from the aggregate. So typically what people say is the ITZ thickness is around 50 microns. But here you see that 50 microns could be from one aggregate 50 microns this way, and from the other aggregate 50 microns this way. But you see here between aggregates you have hardly 100 micron space in most cases. So there are ways in which you can actually show that ITZ is maybe an artifact of the way that you are preparing your specimen, way that you are mixing your concrete and so on and so forth. But there are arguments which are supportive of ITZ also. I will show you later when it comes to strength and durability studies that our understanding of ITZ as the layer of paste around the aggregate, which is much weaker than the rest of the paste, seems to be quite strong because it supports a lot of the other experimental observations that we actually notice. And that we will look at when we actually get to this discussion of strength and durability. But for now, you need to understand that the concept of ITZ, even though we proclaim that's the weakest link in concrete that leads to the difficulties in concrete properties and so on and so forth, there is a group of people around the world, a group of researchers, well-known researchers, who seem to negate that idea that ITZ is even present. So you need to ensure that you understand both sides of the story. Okay? But later I will show you positive evidences of why ITZ can have very distinct effects on the performance of concrete. Okay. But what you do see in this picture is the porosity that is available in the paste. Okay. I am not talking about this void here. That void is probably because of the effects of mixing. Okay. If you have mixed and compacted well enough, maybe that void will go. But I am talking about the porosity inside the paste, the extremely fine pores that is distributed within the paste. That is your capillary porosity. This one here, this spherical appearing void is just a void, it is not a capillary. Okay. So we will look at how we distinguish voids and pores a little bit later. Now a very important part of our understanding of the cement paste is our understanding of in what different ways is water held within the cement paste. Because this movement of water within cement is responsible for a lot of issues that are actually noticed with respect to concrete performance. Okay. So obviously there is porosity inside the paste, so water is held within the pores. So water which is held within the capillary pores is the capillary water. Water which is held within the gel pores is called gel water and is composed of two types. One is called adsorbed water, the other is called interlayer water. And finally, of course, there's water which is within the structure of the CSH or within the structure of calcium hydroxide or within the structure of ettringite or monosulphate. That's the bound water. Remember, we write CSH as calcium silicate hydrate. That bound water corresponds to the hydrate portion of the CSH. Okay. But apart from this, there's free water available in the system, and that free water depends on the size of the porosity, will be called as gel water or capillary water. Okay. So capillary water is present in voids generally larger than 50 angstroms. So here it says 5 nanometer, but the general definition is 10 nanometer. Okay. Today people seem to agree that 10 nanometer is the size that defines capillary porosity. Now if you look at this capillary water, you can further distinguish this capillary water into water that is present in larger porosity and smaller porosity. So when you dry out water from larger pores, will there be a lot of strain associated with that? Again, same issue, pressure is inversely proportional to diameter. When the diameter of the pores is large, the capillary pressure upon drying will be less, right? On the other hand, when you start drying out water from very small pores, the capillary pressures will be very high, associated shrinkage strain will be very high. Okay, so again, you can classify the capillary water into free water, the removal of which does not cause any shrinkage, or you can call it as water held by capillary tension in small pores, which results in very large shrinkage strains upon drying. So already now you understand that if you have excess water present in the system, some of it may be present in these very large pores. So you may cause sufficient drying to happen without any shrinkage in the system. Okay. So sufficient drying implying the concrete may start losing mass because of drying, and that water is actually coming out of the larger pores, so you do not create any shrinkage strains in the system. It is only when you start drawing this water from smaller pores do you result in very high shrinkage levels in the system. Now of course when you are coming to gel pores, you are already coming to very small porosity, because of which if you start drying out gel pores, you can imagine that that is going to create massive shrinkage in the system. So gel porosity is again classified into, or water is classified into adsorbed water and interlayer water. So this seems to suggest that part of the water which is present in the CSH is adsorbed on the CSH particles. What do you mean by adsorption? Sticking to the surface. Okay. Absorption means they are going inside. Adsorption means sticking to the surface, and then interlayer water means it is something indicating between layers of CSH. So already we are sort of assuming a certain type of a structure for CSH, okay, and what do you assume the structure as? If it is going to be adsorbed on a surface and between layers, so what is the best model that we can come up with for CSH? A sandwich sort of a structure, maybe sheet like structure. So this sort of tells us that CSH has a sheet like structure, because of which water gets adsorbed on the layers and is also present between the sheets. Now this makes it more easy to imagine what happens when you remove this water. When you start removing the water from the surface of the sheets, you may cause wrinkling of the sheets. When you start removing the water from between the layers, it will lead to collapse of the layers. So that will lead to very high levels of strains in your system. Okay. So this adsorbed and interlayer water are together known as gel water, and the removal of this gel water will be associated with massive shrinkage in your system. Of course, the bound water is something that is within the structure of the product. Simply heating your cement paste will not release this bound water. All the first three types of water, if you simply take your cement paste and heat it to 105 degrees Celsius, you will remove all that water. But the water that still remains after 105 heating is bound water, because that is something which you cannot remove by heating, you have to remove it by ignition. You have to burn it up to about 1000 degrees Celsius, typically 600, but mostly we do loss on ignition tests all the way up to 1000 degrees Celsius. So it's usually enough to heat it up to 600, but we generally want to ignite it to about 1000 degrees Celsius. The mass difference between what is ignited at 1000 and what remains after drying at 105, that's called non-evaporable water. Okay, so you have two types of water, evaporable water and non-evaporable. So evaporable water is what can dry out when you heat it to about 105 degrees Celsius. Why 105? Yeah, because boiling point is 100. So at 105 you are sure that all that water will go out. Okay. So
but the pressure in the size of the pores are less, so the pressure there will be different than the normal pressure 100 degree what we talk.
okay. So you are saying that the boiling of water within the porosity may not exactly happen at 100. Yes, that's correct. There may be a slightly higher temperature that you require because of the high pressures with which this water is held. Absolutely. The same will apply when we talk about freezing, because the pores are extremely small. Water does not freeze at 0 degrees Celsius inside the pore. So you'll have to actually depress the freezing point further to really cause that water to freeze. Correct. So this boiling point also may actually be much higher than 100, but we generally assume that by 100 we are removing the water which is evaporable. The later part, which is non-evaporable, you go from 100 to 1000 degrees Celsius and look at the mass loss and attribute that to the hydration products. Now, not all hydration products last all the way at 1000 degrees Celsius. CSH, for example, the bound water in CSH starts going beyond 100 itself, and by about 300 degrees Celsius this bound water in CSH is mostly gone, and then you start seeing some mass changes because of structural changes in the CSH. Calcium hydroxide remains stable all the way up to about 450 degrees Celsius. Only at 450 the calcium hydroxide starts losing its water and transforms to calcium oxide, right? At 450 degrees Celsius that water goes out and it becomes calcium oxide. Okay. Now primarily the reason why concrete is able to resist temperature is because all compounds in concrete or all compounds in cement paste do not deteriorate until you reach temperatures of more than 500 degrees Celsius. Okay. Other compounds like ettringite or monosulphate, they may start disintegrating much earlier, like even 100 to 150 degrees Celsius. Most of your ettringite will deteriorate or disintegrate. Monosulphate, on the other hand, there are some compounds within monosulphate that can last for much longer, but generally you see that by about 5 to 600 degrees Celsius all the waters which are held, bound water which is held within the structure of the hydration products, that will go away at about 600 degrees Celsius. Now generally why we go up to 1000 is that invariably cement also contains some limestone, calcium carbonate. Where is that coming from? During the manufacture of Portland cement we are also adding limestone as a performance improver, and very often what may also happen is that this calcium carbonate phase may still form from cement which is hydrated because of the action of carbon dioxide from the atmosphere. So this calcium carbonate we saw earlier gets completely decomposed only at about 900 degrees Celsius. Remember we talked about this kiln reaction in which the limestone decomposes to release calcium oxide, that happens between 7 and 900 degrees Celsius. So depending on the purity and the form of the calcite that is actually forming, this carbon dioxide from calcite gets decarbonated at about 900 degrees Celsius. So that is why we actually go all the way up to 1000 to determine the extent of mass change that actually happens when cement paste is heated over a large temperature range. Okay, so now what we will do is we will try to work out, based on an initial composition of the cement paste, what is the composition of your hydrated cement paste in terms of what is the extent of porosity that is forming in this system. So for this we will have to do some assumptions, and these assumptions are based on properly formulated experiments which have helped us determine these quantities quite accurately. Okay. First of all, theoretically 0.23 grams of bound water is required to completely hydrate 1 gram of cement. So if we take 1 gram of cement and say that 100% hydration is happening, then that 1 gram of cement needs exactly 0.23 grams of water. In other words, 0.23 is the water cement ratio that is required to completely hydrate 1 gram of cement, or required to hydrate cement. Now whatever extra water that we add in the system fills up first the gel pores, and then it will fill up the capillary pores. Okay. When cement hydrates, when cement reacts with water, the resultant product that forms has a lower volume as opposed to that of the reactants. Okay. And this decrease, volume decrease, is equal to 25.4% of the bound water content. So let us assume a cement which is 100% hydrating. Okay. If I have 1 gram of cement that hydrates 100%, that means how many grams of bound water I have? 0.23. 0.23 grams of bound water is same as 0.23 milliliters of bound water, because density of water is 1 gram per milliliter. That means your volume decrease is how much? 25.4% of 0.23 milliliters. That is about 0.06 milliliters for every gram of cement that is hydrating. Okay. Generally what is assumed is you have about 6 to 8% volume change or volume decrease when 1 gram of cement actually hydrates. 6 to 8% volume change. Okay. And where is this volume change going? What is it creating in the system? It is creating the porosity in the system. Okay. Now what is also needed for calculation is the characteristic porosity of the hydrated CSH gel. In other words, that is nothing but the volume of pores divided by volume of pores plus volume of solid CSH into 100, that is equal to 28. Now how is that determined? Obviously there is some experimental evidence that seems to show that if you have pure CSH and you study the porosity by an appropriate methodology, mostly what is done is they have methodologies that are based on sorption, okay, adsorption, and based on that they have worked out that the characteristic porosity of CSH is 28%. So volume of pores to the total volume, the ratio of that is 28%. Okay. Total volume is porosity plus solid CSH. Now given this background information, let us now try to calculate what would happen in a cementitious system at a high water cement ratio, let us say 0.5. So let us say our water cement ratio is 0.5, we assume 100% hydration and no drying of this water out of the cement paste. So we are conducting this experiment in an insulated environment and there is no drying. Okay. So what we want to calculate is what is the volume of capillary porosity in the system. So let us first look at the volume of the reactants. So cement is 100 grams, let us say we start with 100 grams of cement. So volume of cement is 100 divided by density, that is 3.15 grams per cubic centimeter or gram per milliliter, that is 31.8 milliliter. The cement has a volume of 31.8. Okay. Mass of water is 50 grams because we have water cement ratio of 0.5. So that is volume of water is the 50 milliliters. All clear so far? Okay. Now we say that 100% hydration has happened. That means every part of cement is reacted. So 100 grams of cement is reacted. So we have 23 grams of bound water or 23 milliliters of bound water volume is present. What do we do next? We calculate what the volume decrease is because of this reaction, right? That volume decrease should compensate or should be taken into the calculation of the solid hydrated cement paste. So volume of the solid hydrated cement paste is equal to volume of cement plus volume of bound water minus the volume decrease that happens upon hydration. Okay, all with me so far? So volume of solid hydrated cement paste is equal to the volume of cement, because all of it is reacting. We have to take the entire volume of cement plus volume of the bound water in the cement, that is 23 milliliters, minus the volume decrease that is happening upon hydration, that is equal to 0.254, 25.4% of the bound water content, 23 milliliters. So this works out to 48.9 milliliter. Okay. So what now? Our next aspect is to look at what the total volume of the hydrated cement paste is. So we know that 28% is the characteristic porosity, that is equal to volume of gel pores by solid HCP plus gel pores. Why gel pores only? Why not capillary pores? We are only considering CSH. We are only considering the volume of solid hydrated cement paste in the CSH. So when we write this formula, we can find out that volume of gel pores is 19 milliliters. Now one important aspect that you need to understand here is that 19 milliliters is now the additional volume of water that is absolutely required in the system for obtaining a 100% hydrated cement paste. Only if this 19 ml of extra water is present will my hydrated cement paste be composed of a properly hydrated CSH and all the pores filled inside with water. So what does that tell you about systems which have 0.42 water cement ratio or higher? If my water cement ratio in the system is 0.42 or higher, I can get theoretically a system that hydrates completely. If I have anything less than 0.42, some part of cement only will hydrate, okay, because when I am creating the hydrated product, I also have to create the gel porosity.
Why is it required?
No, see again, what do you mean? See again, what will happen is if that gel pores are not filled with water. For example, why is the gel pore created? Because you are creating CSH, right? And if you don't have sufficient water to create the associated wet gel porosity, that means you don't have enough water to hydrate the cement.
But we've already provided 0.23 which is required for hydrate.
No, 0.23 is the bound water content. So the hydrated cement paste will have bound water plus gel porosity. For the cement paste to form as a mass, the water should be sufficient to bind with the paste and have a 100% humidity atmosphere provided in the gel porosity, and that is being provided by this extra 19 milliliters. So for now what we understand is to hydrate cement and produce a properly bound structure of CSH, I need to have the additional 90 milliliters of porosity also to be filled up with water. Okay, so what is happening now? I have 48.9 milliliters of solid HCP. I have 90 milliliters of gel water. Okay, so the total volume becomes equal to 67.9 milliliter. That means volume of hydrated cement paste now is 67.9 milliliter. What is the original volume? Original volume is 31.8 plus 50. That is 81.8 milliliter. Because I had 31.8 as the volume of cement, 50 is the volume of water. But now I have only 67.9. So all my remainder capillary porosity equal to total volume of reactant minus total volume of the hydrated cement paste that is forming. So let's say you have your system here. It's got some cement and some water. Okay, that's the reactant system. The products are on this side. I have the products here. I have solid HCP. I have gel pore and I have the capillary. Okay.
Product I'm taking 50 grams of water and 100 gram 31.8 ml of
Cement.
The
Yeah.
total volume will come to 81.8.
Yes.
It will not reduce.
That volume has to be the same in your product also. The distribution of your phases in that volume will change. In the past you had 31.8 ml occupied by solid. Now of course you know that this solid is going to react with the water and it's going to be spread throughout the system as a network of hydrated products. But the network of hydrated products is only actually occupying this much solid volume. Okay? And additionally it's got this volume of the gel porosity. All the remainder which is left in this space is the capillary porosity. Okay? So this volume decrease upon hydration is accounted for in the calculation of the solid HCP volume. The remainder of it will go into the porosity. It is forming porosity basically, that is what we are trying to say. So now 13.9 milliliters of capillary porosity is available, but how much extra water is available?
8 ml.
Only 8 milliliters, because 23 went here to the bound water, 19 went to the gel water, remainder is 50 minus 23 minus 19, that is 8 milliliters. And the remainder of the capillary porosity is empty. It is air filled. So there is partly water filled porosity, that is partly air filled porosity. What may also happen is, if you are doing wet curing of this concrete, what will happen? The remainder 5.9 milliliter may also start getting filled up with water, but that will happen only in the early ages, because that is when the porosity will be large enough for curing water to enter. But later, maybe as early as about 2 to 3 days, your system may be watertight enough for outside water, curing water, preventing curing water from entering the concrete. Okay? So what we are saying is, with this assumption, we are actually able to work out the approximate amount of capillary porosity in the system. Now there is an interesting problem. You see here that 0.42 is the absolute minimum required to ensure that 100% hydration takes place. Now we know that by increasing or by reducing the water to cement ratio below 0.42, we are going to be reducing the amount of hydration that is happening in the system. But we know that reduction in water cement ratio is important to produce a concrete that is stronger and more durable. So what do you think should be affected here? Essentially, the capillary porosity is getting reduced. And one more important part is, when you move to a lower water cement ratio system, your products will contain the solid HCP, the gel pore, capillary pore, and one more ingredient, unhydrated cement. Okay? That means it is also part of your solid structure now, which is why your capillary porosity is reducing. And that example is actually worked out in the next slide, but we are out of time for today. We will resume our discussion tomorrow morning and complete this segment on cement chemistry.